Tonight, we're going to explore something that sounds simple, but is actually one of the most mind-bending concepts in all of physics: the speed of light. You've probably heard this number before. Maybe you remember it from school. 186,000 miles per second. Scientists throw this number around constantly when talking about the universe. But here's what most people don't realize. When you actually understand what the speed of light means, when you truly grasp what happens when objects approach this speed, it changes how you see the universe. It's not just a fast speed. It's not just some number Einstein used in his equations. It's a cosmic speed limit built into the fabric of reality itself. And the consequences of that speed limit are so strange, so counterintuitive, that they challenge our ability to comprehend them. This is the story of a single number that took humanity 400 years to measure. And once we finally did, it shattered everything we thought we knew about time, space, and reality itself. By the end of this journey, you're going to understand why time slows down for moving objects, why space itself shrinks, why two people can disagree about whether events happen at the same moment and both be completely correct, and why, no matter how advanced our technology becomes, we may never be able to visit even the nearest stars in a human lifetime. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive in. For most of human history, people assumed light traveled instantaneously. And honestly, that makes perfect sense based on everyday experience. When you flip a light switch, the room illuminates. There's no delay you can perceive. When lightning strikes, you see the flash immediately. The thunder takes time to reach you, sure, but the light appears the moment the bolt strikes. So it seemed obvious that light must travel infinitely fast. It just arrives. The ancient Greek philosopher Empedocles, who lived around 490 to 430 BCE, was one of the first people to question this assumption. He proposed that light was something in motion and therefore must take time to travel from place to place. But his contemporary Aristotle dismissed this idea entirely. Aristotle argued that light propagation was instantaneous. And because Aristotle's word carried enormous weight in Western thought for over 2,000 years, his view dominated. If Aristotle said light was instantaneous, then light was instantaneous. Case closed. In the Islamic world, the scholar Al-Haytham, also known as Ibn al-Haytham, proposed in his 1021 work called The Book of Optics that light takes time to travel from one place to another and moves at different rates through different materials. This was remarkably insightful for its time, but without any way to actually test this idea, it remained speculation. You can have the right answer, but without evidence, it's just a guess. The first person to actually attempt measuring light's speed was Galileo Galilei. In his 1638 book, Two New Sciences, Galileo described an experiment that sounds almost comically simple. Two observers would stand on distant hilltops near Florence, each holding a covered lantern. The first observer would uncover their lantern, and the moment the second observer saw the flash, they would uncover theirs. By measuring the time between uncovering the first lantern and seeing the return flash, Galileo hoped to calculate how long light took to travel the round trip. Galileo tried this at distances of less than a mile, but detected no delay whatsoever. He correctly concluded that light is, if not instantaneous, extraordinarily rapid. Here's why the experiment was doomed to fail. Light travels 1 mile in approximately 5 microseconds. That's 5 millionths of a second. Human reaction time, however, is around 200,000 microseconds. Think about what that means. The delay Galileo was trying to measure was 40,000 times smaller than the error introduced by human reflexes. It was like trying to measure the weight of a single grain of sand using a bathroom scale. The tool simply wasn't sensitive enough for the measurement. The Accademia del Cimento repeated Galileo's experiment in 1667 with the same null result. Measuring light's speed would require something other than human reflexes. It would require looking much, much farther away. It would require astronomical distances. The breakthrough came from an unexpected source, the moons of Jupiter. Ole Christiansen Romer was a Danish astronomer born on September 25, 1644. In the 1670s, he was working at the Paris Observatory under the famous astronomer Giovanni Cassini. Romer's job was to create precise tables predicting when Jupiter's moon Io would disappear behind Jupiter. These events, called eclipses, happened with clockwork regularity. They were useful for navigation, and accurate predictions were valuable to sailors trying to determine their longitude at sea. But as Romer compiled his observations over months and years, he noticed something strange. The eclipses weren't happening exactly when predicted. When Earth was moving toward Jupiter in its orbit, the eclipses seemed to occur slightly early. When Earth was moving away from Jupiter, they occurred slightly late. Over the course of a year, these timing differences accumulated into a significant discrepancy. Romer realized there was only one explanation that made sense. Light took time to travel. When Earth was closer to Jupiter, there was less distance for the light to cross, so observers saw the eclipses sooner. When Earth was farther away, the light had to travel a greater distance, causing delays. The eclipses themselves were happening like clockwork. But the light carrying news of those eclipses had to cross different distances depending on where Earth was in its orbit. Think about what Romer was realizing. He wasn't seeing the eclipses as they happened. He was seeing them after a delay that depended on distance. It was like watching fireworks from across a valley and noticing the sound arrives later than the flash. Except here, even the flash was delayed. The light itself needed time to cross the vast gulf of space. On August 22, 1676, Cassini announced to the Academy of Sciences that future eclipse predictions would incorporate corrections for light travel time. Then, in September of that year, Romer made a bold prediction. He calculated that the eclipse of Io, scheduled for November 9th, would occur 10 minutes later than the standard tables predicted. Think about how audacious this was. Romer was essentially saying, I know when this eclipse will happen better than the official predictions, and the reason is that light takes time to travel. If he was wrong, he'd look foolish. If he was right, he'd have proven something fundamental about the nature of light. On November 9th, 1676, astronomers watched and waited. The eclipse occurred at 5:35 and 45 seconds in the morning, exactly 10 minutes late, precisely as Romer had predicted. On November 21st, 1676, Romer presented his findings to the French Academy of Sciences. On December 7th, his work was published in the Journal des Savants. This was the first successful measurement of light speed in human history. Romer estimated that light takes 22 minutes to cross the diameter of Earth's orbit around the Sun. This gave him a speed of approximately 140,000 miles per second. He was off by about 24 to 25%, mainly because astronomers at the time didn't know the precise size of Earth's orbit. But he had proven what Aristotle got wrong. Light doesn't arrive instantly. It races across space unimaginably fast, but it still takes time to get where it's going. It would take 53 years for independent confirmation, 53 years before someone else proved Roma right through a completely different method. In 1728, English astronomer James Bradley discovered something called stellar aberration while searching for a completely different phenomenon. Bradley was trying to detect the slight shift in star positions caused by Earth orbiting the Sun, called stellar parallax. This was an important measurement because it would provide direct evidence that Earth actually moved around the Sun, something that was widely accepted but still not proven by direct observation. What Bradley found instead was that stars appeared to shift position by about 40 arcseconds over the course of a year, but in the wrong direction and wrong timing for parallax. The stars seemed to be displaced in the direction Earth was moving at any given moment. The explanation came, legend says, while sailing on the Thames River. Bradley noticed that the direction of the wind relative to his boat seemed to change when the boat changed direction, even though the actual wind hadn't shifted. He realized stars behave the same way. Picture walking through a snowstorm. Even if the snow is falling straight down, you have to tilt your umbrella forward to stay dry because you're moving into the falling snow. Starlight does the same thing. It appears slightly displaced in the direction of Earth's orbital motion. This phenomenon only makes sense if light takes time to travel. If light arrived instantly, there would be no aberration. The fact that aberration exists and has a specific measurable angle allowed Bradley to calculate light's velocity. By measuring this displacement and knowing Earth's orbital speed, Bradley calculated light's velocity at between 183 and 187,000 miles per second. He was within 2% of the modern value, and he had independently confirmed what Römer discovered half a century earlier. Light has a speed, and that speed, while almost unimaginably fast, is finite and measurable. The next major advance came from trying to measure light's speed here on Earth without relying on astronomical distances. This was the challenge that had defeated Galileo. How do you measure something that travels a mile in 5 millionths of a second using equipment you can set up in your local area? Armand Hippolyte Louis Fizeau was a French physicist born on September 23, 1819. On July 23, 1849, he performed an elegant experiment and announced the results to the Académie des Sciences in Paris. Fizeau set up a light source on a bell tower in Suresnes, a suburb west of Paris. About 5.4 miles away on Montmartre Hill, he placed a mirror. Between the light source and the mirror, he positioned a toothed wheel with 720 teeth. Here's how it worked, and it's genuinely clever. Light from the source passed between two teeth of the wheel, traveled to the distant mirror, bounced back, and returned to the wheel. If the wheel wasn't spinning, or spinning slowly, the returning light would pass back through the same gap and reach the observer's eye. But if the wheel was spinning at just the right speed, by the time the light returned, the wheel would have rotated enough that a tooth blocked the path. The light would be cut off. By carefully adjusting the wheel's rotation speed, Fizeau could find the exact speed where the returning light was blocked, and then the speed where it passed through the next gap. He found that at 25.2 rotations per second, the returning light passed through the next gap over from where it started. From this, knowing the wheel's rotation speed, the number of teeth, and the total distance the light traveled, he could calculate light's velocity. His result was about 194,600 miles per second. This was about 4.5% too high, but it was a triumph nonetheless. For the first time, Light speed had been measured without relying on the vast distances of the solar system. The cosmic could be measured in a laboratory. Galileo's dream had finally been achieved, 2 centuries after he first proposed the experiment. Fizeau's former collaborator and rival, Léon Foucault, developed an even more refined technique using rotating mirrors instead of toothed wheels. In 1862, Foucault measured light speed at about 185,000 miles per second. This was only 0.6% different from the modern accepted value, remarkably precise for equipment built over 160 years ago. But Foucault had done something even more important 12 years earlier. On April 27, 1850, he demonstrated that light travels slower in water than in air. This might seem like a minor detail, but it was actually decisive evidence in one of physics' longest-running debates. Isaac Newton had proposed that light consisted of tiny particles, which he called corpuscles. According to Newton's theory, light should travel faster in denser materials like water because the particles would be pulled in and accelerated. The competing wave theory predicted the opposite. Light waves should slow down in denser media, just as sound waves behave differently in different materials. Foucault's 1850 experiment showed conclusively that light travels slower in water. As one historian put it, this result drove the last nail in the coffin of Newton's particle theory of light. Light behaved as a wave. Newton, for all his genius, had gotten this one wrong. Even the greatest minds can be mistaken. The quest for ever greater precision led to Albert Abraham Michelson, an American physicist born on December 19, 1852. Michelson's family emigrated from Prussia when he was 2 years old. At 17, he received an appointment to the United States Naval Academy directly from President Ulysses S. Grant. Michelson became obsessed with precision measurement. In 1878 and 1879, while stationed at the Naval Academy in Annapolis, Maryland, he refined Foucault's rotating mirror technique and obtained a value of about 186,350 miles per second. This was the most accurate measurement of light speed in history up to that point. But Michelson's most famous experiment wasn't about measuring how fast light travels. It was about measuring something that turned out not to exist at all. And this experiment would accidentally pave the way for the most revolutionary theory in the history of physics. In the late 19th century, physicists believed that light waves, like sound waves, needed a medium to travel through. Sound requires air or water or some physical substance to propagate. You can't hear anything in a vacuum because there's nothing for the sound waves to travel through. So what did light waves propagate through? What carried them across the emptiness of space from the sun to Earth? Scientists proposed the existence of a substance called the luminiferous ether, an invisible, weightless material that filled all of space and carried light waves the way air carries sound. This ether had to have peculiar properties. It had to be rigid enough to transmit waves at enormous speed, yet fluid enough not to impede the motion of planets through it. It had to be everywhere, filling all of space, yet completely undetectable by any ordinary means. If the ether existed, and if Earth moved through it as our planet orbited the Sun, then light should travel at slightly different speeds depending on direction. Light traveling in the direction of Earth's motion through the ether would be swimming against the current, so to speak, and should arrive slightly slower. Light traveling perpendicular to Earth's motion wouldn't face this resistance. The difference would be small, but with sensitive enough equipment, it should be detectable. Michelson designed an instrument called an interferometer to detect this difference. The device split a beam of light into 2 perpendicular paths, bounced each beam off mirrors, and recombined them. If one path was faster than the other, the recombined beams would be slightly out of sync, creating an interference pattern that could be measured with extreme precision. In 1887, Michelson teamed up with Edward Williams Morley, a chemistry professor at Western Reserve University in Cleveland, Ohio. They set up the experiment in the basement of Adelbert Dormitory. To isolate the apparatus from vibrations, they mounted the interferometer on a large sandstone slab floating in a pool of mercury. The effective path length was about 36 feet, achieved through a complex arrangement of 16 mirrors. The experiment used monochromatic yellow light from a sodium lamp with a wavelength of about 589 nanometers. Based on their calculations, they expected to see a fringe shift of approximately 0.4 fringes as they rotated the apparatus to different orientations. This would be clear evidence of Earth's motion through the ether. From April through July of 1887, with key observations on July 8th, 9th, and 11th, Michelson and Morley conducted their measurements. The result was essentially nothing. The measured displacement was less than 1/40th of what they expected. In August 1887, Michelson wrote to the British physicist Lord Rayleigh with the words, "The result is decidedly negative." This is often called the most famous failed experiment in scientific history. Michelson and Morley had set out to measure Earth's motion through the ether, and instead proved that the ether didn't exist, or at least didn't affect light the way everyone assumed. Light traveled at exactly the same speed in every direction, regardless of Earth's motion through space. No matter which way you pointed your apparatus, no matter what time of year, no matter how carefully you measured, light always traveled at the same speed. For his precision optical instruments and the investigations they enabled, Michelson received the Nobel Prize in December 1907. He was the first American to win the Nobel Prize in any science. The Michelson-Morley experiment had raised a deep puzzle. If there was no ether, what carried light waves? And why didn't Earth's motion affect light's speed? The answer would require completely rethinking our understanding of space and time. It would require a revolution. Interestingly, during the intense preparation for this experiment in September 1885, Michelson suffered a mental breakdown. His collaborator Morley attributed it to the pressure. He recovered by October 1885, but the episode shows just how much was riding on these measurements, how desperately physicists wanted to understand the nature of light. In October 1983, the 17th General Conference on Weights and Measures made a decision that would have seemed absurd to earlier generations of scientists. They stopped trying to measure the speed of light. Instead, they defined it. The official definition fixed the speed of light at exactly 186,282.397 miles per second, with zero uncertainty. By definition, the meter is now derived from the speed of light, not the other way around. This might seem like cheating, but it actually makes deep sense. After centuries of ever more precise measurements, scientists had come to understand that the speed of light isn't just a number we measure. It's a fundamental constant of nature, woven into the fabric of space-time itself. It made more sense to use this constant as a foundation for other measurements than to keep trying to pin it down more precisely. The speed of light in a vacuum is now as exact as the number of eggs in a dozen. It's not something we measure anymore, it's something we know. In 1905, a 26-year-old man working at the Swiss Patent Office in Bern published 4 papers that transformed physics. His name was Albert Einstein, and he had no university position, limited access to scientific reference materials, and no laboratory. He called the patent office "that secular cloister where I hatched my most beautiful ideas. Einstein's main intellectual companion was a colleague named Michel Besso. Einstein later wrote that he could not have found a better sounding board for my ideas in all of Europe. They would walk home together after work, discussing physics, debating ideas, working through problems. And from these conversations, some of the most important insights in scientific history emerged. The year 1905 is known as Einstein's Annus Mirabilis, or Miracle Year. The 4 papers he published in the German journal Annalen der Physik addressed completely different topics, and any one of them would have secured his place in scientific history. The first paper, received on March 18th and published on June 9th, explained the photoelectric effect and proposed that light comes in discrete packets of energy, which we now call photons. This work would eventually win Einstein the Nobel Prize. The second paper, received on May 11th and published on July 18th, provided mathematical proof that atoms exist by explaining the random motion of tiny particles suspended in liquid called Brownian motion. The third paper, received on June 30th and published on September 26th, was titled On the Electrodynamics of Moving Bodies. In German, Zur Elektrodynamik bewegter Körper. This 31-page paper introduced the special theory of relativity. It would eventually overturn our understanding of space, time, and causality. The fourth paper, received on September 27th and published on November 21st, was just 3 pages long, but contained perhaps the most famous equation in science. In it, Einstein showed that mass and energy are equivalent, related by a factor of the speed of light squared. Think about what Einstein accomplished that year. He was 26 years old. He had no academic position, no laboratory, no research assistants. He worked 6 days a week, examining patent applications for inventions. And in his spare time, during evenings and weekends, he rewrote the foundations of physics. 4 revolutionary papers in a single year. Any one of them would have made him famous. Together, they made him immortal. Let's focus on that third paper, because it's the one that explains why the speed of light breaks reality. Einstein had been troubled by a thought experiment since he was about 16 years old, sometime around 1895 or 1896. He described it decades later in his autobiographical notes, written in 1946. A paradox upon which I had already hit at the age of 16. If I pursue a beam of light with a velocity c, I should observe such a beam of light as an electromagnetic field at rest, though spatially oscillating. There seems to be no such thing, however, neither on the basis of experience nor according to Maxwell's equations. Think about what Einstein was imagining. A teenager picturing himself running alongside a beam of light, matching its speed, looking over at the light to see what it looked like. If he could do that, what would the light look like? According to Newton's physics, he should see a frozen wave, a stationary ripple in the electromagnetic field, just sitting there next to him as they traveled together through space. But James Clerk Maxwell's equations describing electromagnetism didn't allow for such a thing. Maxwell's equations predicted that electromagnetic waves, including light, must always travel at a specific speed. Frozen light, stationary light, light moving at any speed other than the speed of light, simply wasn't physically possible according to these equations. This paradox nagged at Einstein for years, a decade of wondering, thinking, turning the problem over in his mind. The solution he eventually reached was radical. Maybe the premise was wrong. Maybe it wasn't possible to run alongside a beam of light at all. Maybe light always travels at the same speed relative to any observer, no matter how fast that observer is moving. Einstein built his special theory of relativity on two fundamental assumptions, or postulates. The first postulate, which he called the principle of relativity, states that the laws of physics are the same in all inertial reference frames. An inertial reference frame is just a viewpoint that isn't accelerating. If you're on a smoothly moving train with the windows covered, no experiment you perform inside the train can tell you whether you're moving or stationary. All motion is relative. There's no absolute state of rest. There's no cosmic background against which motion can be measured. There's only motion relative to other objects. The second postulate states that light always propagates in empty space at the same definite velocity, regardless of the motion of the light source or the observer, whether you're moving toward a light source or away from it. Whether the source is moving toward you or away from you, you'll always measure light, traveling at exactly the same speed, 186,282 miles per second. These two postulates seem almost reasonable when stated individually. The first one had been around since Galileo. The second one was essentially what the Michelson-Morley experiment had shown. But together, they have consequences that violate everything we think we know about how the world works. Consider this situation. You're on a train moving at half the speed of light. That's about 93,000 miles per second. You turn on a flashlight and shine it toward the front of the train. Common sense says that from the perspective of someone standing on the platform watching the train pass, that light beam should be traveling at 1.5 times the speed of light. The train's speed plus the light's speed. That's how velocities add, right? If you're on a bus going 50 miles per hour and you throw a ball forward at 20 miles per hour, someone on the sidewalk sees the ball moving at 70 miles per hour. Speeds add, but Einstein's second postulate says no. The person on the platform will measure that light traveling at exactly the speed of light. Not 1.5 times, just the speed of light. The same speed you measure on the train. How can this possibly be true? How can both you on the train and the observer on the platform measure the same beam of light traveling at the same speed when you're moving at half the speed of light relative to each other? The answer is that time and space themselves must be flexible. If the speed of light is absolute and constant for all observers, then time and space must adjust to make this possible. Different observers experience time passing at different rates. Objects in motion shrink in the direction they're traveling. Events that one observer sees as simultaneous may not be simultaneous to another observer. This isn't a flaw in our measuring instruments. It's not something going wrong. Time and space genuinely behave this way. And once you accept Einstein's two postulates, all of these strange consequences follow mathematically, inevitably, inescapably. The fourth paper Einstein published that year dealt with the relationship between mass and energy. It carried the unassuming title, "Does the inertia of a body depend upon its energy content?" In just 3 pages, Einstein demonstrated that mass and energy are two forms of the same thing. The famous equation we know as E equals mc squared didn't actually appear in that form in the paper. Einstein wrote it differently, using L for energy and V for the speed of light. If a body gives off the energy L in the form of radiation, its mass diminishes by L divided by V squared. The implications are staggering. Mass can be converted into energy. Energy can be converted into mass. And because the speed of light squared is such an enormous number, approximately 9 followed by 16 zeros in standard metric units, a tiny amount of mass contains an almost inconceivable amount of energy. Think about what this means in concrete terms. 1 pound of matter, if completely converted to energy, would release about 40 quadrillion joules. That's roughly equivalent to a 10 megaton nuclear explosion. The mass of a paperclip, completely converted, could power a city. The energy was there all along, locked inside the mass, waiting. This equation explains why the sun shines. Deep in the sun's core, hydrogen atoms fuse to form helium. The helium weighs slightly less than the hydrogen that made it. Where does that missing mass go? It becomes energy, radiating outward as the sunlight that warms our planet. The sun is slowly converting its mass into energy, about 4 million tons every single second, and will continue doing so for billions of years. The equation also explains nuclear power and nuclear weapons. When heavy atoms like uranium split apart, or when light atoms like hydrogen fuse together, a tiny fraction of their mass converts to energy. The atomic bomb dropped on Hiroshima converted less than 1 gram of matter into the blast that destroyed a city, less than the mass of a paperclip. Einstein himself was not involved in building the atomic bomb. When the Manhattan Project was underway in the 1940s, he was denied security clearance in 1940. But his equation revealed the possibility that was always there, hidden in the relationship between mass and energy. Einstein's special relativity paper was initially met with limited attention. He was, after all, an unknown patent clerk with no academic position. But the German physicist Max Planck recognized the paper's significance and published supportive analysis in 1906. Einstein later wrote that the attention that this theory so quickly received from colleagues is surely to be ascribed in large part to the resoluteness and warmth with which Planck intervened for this theory. Gradually, the scientific community came to understand what Einstein had achieved. But recognition from the Nobel Committee took much longer, and when it came, it wasn't for relativity at all. The Nobel Prize in Physics for 1921 was awarded to Einstein in 1922 for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. Not a word about relativity. Why not? The committee was divided, and one member, a Swedish physicist named Alvar Gullstrand, was actively hostile to Einstein's work. Gullstrand allegedly declared that Einstein must never receive a Nobel Prize, even if the whole world demands it. The solution came from physicist Carl Wilhelm Oseen, who nominated Einstein specifically for the photoelectric effect. By framing it as a proven law rather than a contested theory, Oseen found a way around the objections. The irony deepened at Einstein's Nobel lecture on July 11, 1923. Despite officially receiving the prize for the photoelectric effect, Einstein spoke entirely about fundamental ideas and problems of the theory of relativity. He never once mentioned the photoelectric effect. The committee had given him the prize for the wrong work, and Einstein seemed to know it. There's an interesting story about how Einstein received news of the eclipse observations that confirmed his predictions. In 1919, British astronomer Arthur Eddington led an expedition to observe a total solar eclipse and measure whether starlight was bent by the sun's gravity, as Einstein's general theory of relativity predicted. When the results came back positive, confirming Einstein's predictions, Einstein wrote to his mother on September 27, 1919, "Today some happy news. H.A. Lawrence telegraphed me that the English expeditions have really verified the deflection of light by the sun." Reportedly, when asked what he would have said if the results had been against him, Einstein shrugged dismissively. He was confident in the mathematics. The universe had to work this way. Now, let's dig into exactly how the speed of light breaks our understanding of reality. This is where things get genuinely strange. These aren't speculative ideas or theoretical possibilities. These are measured facts, confirmed by countless experiments over the past century. The universe actually works this way, whether or not it makes intuitive sense. The first consequence of Einstein's theory is called time dilation. When an object moves relative to you, its clock runs slower than yours. Not appears to run slower, actually runs slower. Let me say that again because it's important. A moving clock ticks more slowly than a stationary clock. This isn't an optical illusion. It isn't a mechanical problem with the clock. It isn't a measurement error. Time itself passes more slowly for moving objects. The mathematical formula involves something called the Lorentz factor, named after Dutch physicist Hendrik Lorentz, who worked out many of these equations before Einstein but didn't fully understand their implications. Lorentz thought he was describing how objects contracted as they moved through the ether. Einstein realized there was no ether, and the equations described something more fundamental, the nature of space-time itself. The Lorentz factor depends on how fast something is moving as a fraction of the speed of light. At everyday speeds, the kind of speeds humans experience, it's essentially equal to 1, meaning time passes normally. But as speeds approach the speed of light, the Lorentz factor grows without limit. Let me give you concrete numbers so you can really feel what this means. At 50% of light speed, about 93,000 miles per second, the Lorentz factor is approximately 1.155. This means that for every year that passes on Earth, only about 10.5 months pass for someone traveling at that speed. Not much of a difference in everyday terms, but measurable. At 90% of light speed, the Lorentz factor jumps to about 2.29. 1 year on Earth corresponds to less than 5.5 months for the traveler. Now we're seeing significant time differences. At 99% of light speed, the factor is about 7.09. 1 year on Earth equals only about 52 days for someone moving that fast. More than 6 years' worth of Earth time compresses into a single year for the traveler. At 99.99% of light speed, the Lorentz factor is roughly 71. 1 year on Earth equals about 5 days for the traveler, and at 99.99999% of light speed, the factor is approximately 707. For every year that passes on Earth, someone traveling at that speed experiences only about 12.5 hours. This isn't science fiction. This is measured reality, verified countless times in laboratories around the world. The clocks on GPS satellites, the particles in accelerators, the decay rates of cosmic ray muons, all of them confirm that time dilation is real. To truly grasp how fundamental time dilation is, consider a simple thought experiment called the light clock. Imagine a clock that works by bouncing a beam of light between two mirrors. Each time the light makes a round trip, the clock ticks once. If the clock is stationary relative to you, you see the light traveling straight up and down between the mirrors. But now imagine that clock is moving sideways relative to you at high speed. From your perspective, the light isn't traveling straight up and down anymore. It's traveling in a diagonal zigzag pattern because each time it bounces, the mirrors have moved to a new position. The diagonal path is longer than the straight vertical path, but light always travels at the same speed. So if the path is longer, the journey takes more time. Each tick of the moving clock takes longer than each tick of a stationary clock. This isn't a peculiarity of this particular clock design. Any physical process that can be used to measure time will show the same effect. Chemical reactions, biological aging, radioactive decay, the vibration of atoms, all of these slow down for moving objects. Time itself is slower. Not just clocks, time. The second major consequence is length contraction. Objects moving relative to you are physically shorter in the direction of their motion. This isn't a visual illusion caused by light travel time. The object genuinely occupies less space. The formula for length contraction is essentially the inverse of time dilation. At 50% of light speed, an object contracts to about 87% of its rest length. At 87% of light speed, it contracts to half its rest length. At 99% of light speed, it's compressed to about 14% of its original length. At 99.99%, it's down to about 1.4%. Consider the Stanford Linear Accelerator in California. It's a straight tube about 2 miles long. Inside, electrons are accelerated to very close to the speed of light. From the electron's perspective, because of length contraction, the entire accelerator appears to be only about 20 inches long. The electrons experience themselves as passing through a tunnel shorter than your arm span, even though from our perspective, the tunnel is almost 2 miles long. The electrons genuinely experience a shorter tunnel. From their reference frame, the tunnel really is only about 20 inches long. This isn't a calculation convenience or a theoretical abstraction. It's what actually happens. The universe doesn't privilege one viewpoint over another. There's a famous thought experiment called the ladder paradox, or the barn paradox, that illustrates how strange this gets. Imagine a ladder that's longer than a barn. Someone runs through the barn, carrying the ladder at relativistic speed. From the barn's perspective, the ladder contracts, and for a brief moment, the entire ladder fits inside the barn with both doors closed. But from the ladder carrier's perspective, the barn is contracted, not the ladder, so the ladder shouldn't fit at all. Surprisingly, the universe allows both versions of events to be true. The resolution involves the relativity of simultaneity, which we'll discuss next. What one observer sees as simultaneous, both doors closed at the same moment, is not simultaneous for the other observer. The universe remains consistent, but only if we abandon the idea that there's a single, universal now. The third consequence may be the strangest of all, the relativity of simultaneity. Events that happen at the same time for one observer may not happen at the same time for another observer, moving relative to the first. Einstein illustrated this with a thought experiment involving a train and lightning strikes. Imagine lightning strikes both ends of a moving train at exactly the same instant, from the perspective of someone standing on the platform. That person sees both flashes simultaneously, because the light from each strike has to travel the same distance to reach them. But what about someone sitting in the middle of the train? The train is moving forward. The light from the front strike has a shorter distance to travel to reach them, because they're moving toward where that strike occurred. The light from the rear strike has a longer distance to travel, because they're moving away from where that strike occurred. The passenger sees the front strike first. You might say, well, that's just because of light travel time. The strikes really were simultaneous, and the passenger is just seeing them at different times. But here's the crucial point. In special relativity, there's no way to determine which observer is really correct. Neither perspective is privileged. The universe doesn't have a master clock that everyone agrees on. For the platform observer, the strikes are simultaneous. For the train passenger, they're not. And there's no experiment, no measurement, no appeal to some deeper reality that can settle the dispute. This has a far-reaching implication that takes some time to fully absorb. There is no universal now. Different observers, moving relative to each other, literally live in different versions of the present moment. The British physicist Roger Penrose illustrated this with what's called the Andromeda paradox. Imagine two people passing each other on the street. One is walking slowly toward the Andromeda galaxy, roughly 2.5 million light-years away, about 9.5 quintillion miles. The other is walking slowly in the opposite direction. Their relative velocities are tiny, maybe 11 miles per hour. But because of the vast distance involved, their planes of simultaneity are tilted relative to each other. What counts as now on Andromeda for one person is different from what counts as now for the other. How different? About several days. One person's now on Andromeda might include aliens debating whether to launch an invasion fleet. The other person's now already has them loading the ships. Same moment on Earth. Different events on Andromeda. This isn't practically meaningful for anything we do day to day. The distances and speeds involved in daily life are too small for this effect to matter. But it reveals something unsettling about the nature of reality. The present moment isn't a single instant shared across the universe. It's observer-dependent. It's relative. There is no cosmic now that everyone agrees on. This insight has deep philosophical implications that we'll explore later in this documentary. For now, just sit with the strangeness of it. Two people standing next to each other, disagreeing about what is happening right now in a distant galaxy, and both being completely correct. The most famous illustration of time dilation is the twin paradox. Imagine identical twins. One stays on Earth, the other boards a spacecraft and travels to a star 10 light-years away at 90% of the speed of light, then turns around and comes home. From Earth's perspective, the journey is straightforward. The star is 10 light-years distant. At 90% light speed, the outbound trip takes about 11 years. The return trip takes another 11 years. Total time elapsed on Earth, roughly 22 years. But from the traveling twins' perspective, things are different. Because of length contraction, the distance to the star isn't 10 light-years. At 90% light speed, with a Lorentz factor of about 2.29, the distance contracts to about 4.4 light-years. The trip takes correspondingly less time. Total time elapsed for the traveler, about 9.7 years. When the twins reunite, the traveling twin is approximately 12.5 years younger than the stay-at-home twin. They started the same age. Now one is significantly older than the other. They have experienced different amounts of time. This isn't a metaphor or an illusion. The traveling twin really has aged less. Their heart has beaten fewer times. Their cells have divided fewer times. They have literally lived fewer years. This might seem paradoxical. If all motion is relative, why can't the traveling twin claim that Earth was moving away and returning, which would mean the Earth twin should be younger? The resolution is that the two situations aren't actually symmetric. The traveling twin had to accelerate, first to leave Earth, then to turn around, then to slow down upon return. The stay-at-home twin remained in a single inertial reference frame the whole time. Acceleration breaks the symmetry, and it's the accelerating twin who experiences less time. This is not a theoretical curiosity. It's been measured experimentally. Actual clocks, flown around the world on actual aircraft, have returned showing exactly the time differences Einstein predicted. The twin paradox isn't a paradox at all. It's simply how the universe works. There's one more fundamental consequence of Einstein's postulates. Nothing with mass can ever reach the speed of light. Here's why. As an object speeds up, its kinetic energy increases. But in relativity, energy and mass are related. The more energy an object has, the more it effectively weighs in terms of resisting further acceleration. As the object approaches light speed, the energy required to accelerate it further increases without limit. Think of it like trying to accelerate a car that gets heavier the faster it goes. At first, pressing the gas pedal makes a big difference, but as you approach some maximum speed, each additional mile per hour requires dramatically more fuel. The car responds less and less to the same amount of force. Eventually, you're burning through infinite fuel just to creep toward a speed you can never quite reach. In the relativistic case, as an object approaches light speed, it becomes effectively infinitely massive, requiring infinite force to accelerate it any further. To accelerate an object with mass to exactly the speed of light would require infinite energy. That's not just a lot of energy, it's an amount that cannot exist. The speed of light is an asymptotic limit that can be approached but never reached. To put this in perspective with real numbers, accelerating just 2 pounds of mass to 90% of the speed of light would require about 116 quadrillion joules of energy. That's roughly equivalent to 25 megatons of TNT, more than the largest nuclear weapon ever detonated. And that only gets you to 90%. To reach 99% would require about 550 quadrillion joules. To reach 99.9%, nearly 2 quintillion joules. Each additional decimal place requires dramatically more energy, and reaching 100% would require literally infinite energy. But here's the flip side. Particles without mass must travel at exactly the speed of light. They have no other option. Photons, the particles of light, have no mass. They cannot travel at any speed other than light speed. They're born moving at that speed and never slow down until they're absorbed. Why? Because of the relationship between energy, momentum, and mass in relativity. For a massless particle, the equations demand that it moves at the speed of light. If it didn't, it would have zero energy, which means it wouldn't exist. Light doesn't just happen to travel at a certain speed. It travels at the only speed physics allows for something without mass. The speed of light isn't arbitrary. It's built into the structure of spacetime itself. Before we move on, let's address one more piece of the physics. Relativistic velocity addition. In everyday life, velocities add simply. If you're on a train going 50 miles per hour and you walk forward at 5 miles per hour, someone on the platform sees you moving at 55 miles per hour. This is straightforward addition, and it works perfectly well for everyday speeds. But at relativistic speeds, this simple addition doesn't work. Velocities combine according to a formula that ensures the result never exceeds the speed of light, no matter what velocities you're adding together. Here's an example. 2 spaceships are approaching each other. From Earth's perspective, each one is traveling at 90% of the speed of light. Under simple addition, they should see each other approaching at 180% of light speed. But according to relativistic velocity addition, they actually see each other approaching at about 99.45% of light speed. Extremely fast, but still below light speed. The formula involves multiplying the 2 velocities together, dividing by the speed of light squared, adding 1, and using that as a denominator. The math ensures that no combination of velocities below light speed can ever produce a relative velocity at or above light speed. The universe has a built-in speed limit that cannot be circumvented by any reference frame trick. Understanding these effects requires thinking about space-time as a unified four-dimensional fabric. We're used to thinking of space as three-dimensional and time as something separate, flowing independently in the background. Einstein showed that they're connected, woven together into a single structure called space-time. The person who did the most to develop this mathematical framework was Hermann Minkowski, one of Einstein's former mathematics professors. In 1908, Minkowski gave a famous lecture that began with these words: "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Einstein was initially dismissive of Minkowski's four-dimensional mathematical formulation, calling it superfluous learnedness. But he later came to appreciate its power, and the concept of four-dimensional spacetime became essential to his development of general relativity. One useful tool for visualizing this is the light cone. Imagine a point in space and time, representing an event that happens at a specific place and moment. Now imagine all the light rays that could emanate from that event, spreading outward at the speed of light. In a diagram where time is vertical and space is horizontal, these light rays form a cone shape, opening upward into the future. Everything inside that forward cone represents events that the original event could potentially influence. Light, or anything slower, could travel from the first event to the second. These events are said to be time-like separated, and the second event is in the absolute future of the first. There's also a backward cone, representing all events that could have influenced the original event. These are in its absolute past. But here's the crucial part. Everything outside both cones is called elsewhere. Events in the elsewhere region cannot be causally connected to the original event. Nothing can travel between them, not even light. And here's the strangest part. For events in the elsewhere region, different observers will disagree about which happened first. The order of events outside your light cone depends on how fast you're moving. This is why the speed of light is sometimes called the speed of causality. It's the maximum speed at which cause and effect can propagate. It defines the boundaries of what can influence what. It determines what events are in your future, what events are in your past, and what events are fundamentally disconnected from you, existing in a kind of cosmic elsewhere that you can never reach or influence. The light cone also explains why faster-than-light travel, if it were possible, would create catastrophic logical problems. Imagine you could send a message faster than light. You send a signal to a distant star, and it arrives before light would have gotten there. Now imagine someone at that star is moving relative to you at high speed. Because of the relativity of simultaneity, their now is different from yours. From their perspective, your faster-than-light signal might have arrived before it was sent. If they then send a reply, also faster than light, that reply could arrive back on Earth before you sent the original message. You would receive an answer to a question you haven't asked yet. This is called a causality violation, and it creates grandfather paradoxes, situations where effect precedes cause, potentially allowing you to prevent things from happening that already happened. Most physicists believe that faster-than-light travel or communication is fundamentally impossible, not just beyond our current technology, but forbidden by the structure of space-time itself. The universe seems designed to prevent causal paradoxes. The speed of light isn't just a speed limit. It's a causality limit, protecting the logical order of events across all of space-time. Everything we've discussed so far might sound like elaborate theoretical speculation, How do we know any of this is actually true? The answer is, we've tested it repeatedly, with exquisite precision, and Einstein's predictions have been confirmed every single time. Let's start with the most dramatic direct test of time dilation, the Haffele-Keating experiment. In October 1971, physicist Joseph Haffele of Washington University in St. Louis and Richard Keating of the United States Naval Observatory decided to test the twin paradox with actual clocks. They purchased seats on commercial airline flights and took 4 cesium beam atomic clocks around the world. The eastward trip took place on October 4th, 1971, covering 65.4 hours total with 41.2 hours of actual flight time. The westward trip occurred on October 13th, lasting 80.3 hours total with 48.6 hours in the air. Why did they fly in both directions? Because the effects of special and general relativity had to be separated. Flying eastward, the planes moved in the same direction as Earth's rotation, increasing their speed relative to the cosmic reference frame. Flying westward, they moved against Earth's rotation, decreasing their effective speed. Additionally, at cruising altitude, the clocks experienced weaker gravity than clocks on the ground, which affects time through general relativity. The predictions were specific. The eastward traveling clocks should lose about 40 nanoseconds relative to the ground clocks. The westward traveling clocks should gain about 275 nanoseconds. The results, published in Science magazine in 1972, confirmed Einstein's predictions. The eastward clocks lost 59 nanoseconds, plus or minus 10. The westward clocks gained 273 nanoseconds, plus or minus 7. Both results fell within the predicted ranges. These are tiny time differences, less than a millionth of a second. But they were exactly what relativity predicted, and they represented the first direct macroscopic demonstration that moving clocks really do run slow. The twin paradox isn't just a thought experiment, it's reality. The experiment cost only about $8,000, most of which went to purchasing airline tickets. The clocks were given their own seats, and tickets were purchased for them under the name Mr. Clock. It remains one of the most inexpensive yet definitive tests of fundamental physics ever conducted. An even more dramatic demonstration happens every day in particle physics, laboratories, and even in our atmosphere. Muons are subatomic particles similar to electrons, but about 200 times heavier. They're unstable, decaying into other particles with a half-life of about 2.2 microseconds when measured at rest in a laboratory. That's 2/millionths of a second. In the blink of an eye, literally a muon would undergo thousands of half-lives. Cosmic rays constantly bombard Earth's atmosphere, creating muons about 6 miles up. At 2.2 microseconds per half-life, even traveling at the speed of light, muons should only make it about 2,000 feet before most of them decay. They shouldn't reach the ground in significant numbers, but they do. We detect plenty of muons at Earth's surface. Physicists first noticed this discrepancy in the 1930s and 40s. If you calculate how many muons should survive the trip through the atmosphere based on their rest frame lifetime, you get a number far smaller than what detectors actually measure. The muons seem to be living longer than they should. How is this possible? Time dilation. The muons are traveling at nearly the speed of light. From our perspective on the ground, their internal clocks are running slow. Their 2 microsecond lifetime stretches to many microseconds, giving them enough time to reach us. From the muon's perspective, the explanation is different but equivalent. They're not living longer than 2 microseconds by their own clocks. But from their viewpoint, Earth's atmosphere is length contracted. The 6 miles they need to cross appears as only a few hundred feet. They easily make the trip in their allotted lifetime. This is beautiful. Two completely different explanations, time dilation and length contraction, both giving the same answer. And that answer matches what we actually observe. Both explanations are correct in their respective reference frames, and both are consistent with each other. That's what relativity demands, and that's what nature delivers. In 1977, researchers at CERN conducted a precise test using muons in a storage ring. They accelerated muons to 99.9, 4% of the speed of light, with a Lorentz factor of 29.33. The muons experienced extreme acceleration, about 10 to the 18th times Earth's gravity, as they circled the ring. The measured muon lifetime was 64.419 microseconds, plus or minus 0.058 microseconds. The predicted value from time dilation was about 64.4 microseconds. The agreement was within a fractional error of 2 parts per thousand at 95% confidence. This experiment also confirmed something called the clock hypothesis. Acceleration itself doesn't affect time dilation, only velocity does. Despite the extreme forces on the circling muons, their lifetimes match the predictions based purely on their speed. It's not the acceleration that slows time, it's the velocity. Perhaps the most practical, everyday confirmation of relativity is the global positioning system. The GPS in your phone wouldn't work without relativistic corrections. Every time you use GPS to navigate, you're relying on Einstein's relativity. GPS works by measuring the time for radio signals to travel from satellites to your receiver. Each satellite carries an atomic clock accurate to about 1 nanosecond. By comparing signals from multiple satellites, the receiver can triangulate your position to within a few yards. But here's the problem. The satellites orbit at about 12,500 miles altitude. At that height, they're traveling about 8,700 miles per hour. Special relativity says their clocks should run slower than ground clocks by about 7 microseconds per day because of their velocity. However, at that altitude, gravity is weaker than on Earth's surface. General relativity, Einstein's later and more comprehensive theory, says clocks in weaker gravity run faster. This effect adds about 45 microseconds per day. The net result: satellite clocks run about 38 microseconds per day faster than ground clocks. That might not sound like much, but light travels about 7 miles in 38 microseconds. Without relativistic corrections, GPS positioning errors would accumulate at about 7 miles per day. Within 2 minutes, the system would be useless for navigation. The solution is elegant. GPS satellite atomic clocks are manufactured to tick at a slightly different frequency than ground clocks. Instead of the standard 10.23 MHz, they're set to 10.2299999543 MHz. This pre-compensates for the relativistic time difference, keeping the system accurate. Every time you use GPS to navigate, every time your phone shows you where you are on a map, you're relying on Einstein's relativity. If relativity were wrong, GPS wouldn't work. Another early experimental confirmation came from the Pound-Rebka experiment conducted in 1959 and 1960 at Harvard University. Physicists Robert Pound and Glenn Rebka Jr. set up an experiment in the Jefferson Physical Laboratory Tower using a height of about 74 feet. They shot gamma rays from iron 5-7 atoms at the top of the tower down to a detector at the bottom. According to general relativity, The gamma rays should gain energy as they fall through Earth's gravitational field. This energy gain would shift their frequency slightly higher, a phenomenon called gravitational blue shift. The predicted shift was incredibly small, about 2.5 parts in 10 to the 15th power. To measure such a tiny effect, Pound and Rebke used an elegant technique involving the Mussbauer effect, which allows extremely precise frequency measurements. Their 1960 result was 2.56 plus or minus 0.25 times 10 to the negative 15th, agreeing with the prediction within 10%. A follow-up experiment in 1964 by Pound and Snyder achieved agreement within 1%. This was the first laboratory verification that clocks run at different rates depending on their position in a gravitational field. Before leaving experimental verification, let's talk about what happens when experiments seem to challenge relativity and how science responds. On September 23, 2011, a collaboration called OPERA announced astonishing results. They had measured neutrinos, ghostly particles that barely interact with matter, traveling from CERN in Switzerland to Gran Sasso in Italy, a distance of about 454 miles. According to their measurements, the neutrinos arrived 60.7 nanoseconds faster than light would have. If true, this would overturn everything we've discussed. It would mean faster than light travel was possible, causality could be violated, and a century of physics would need revision. The physics community responded with intense scrutiny. British physicist Jim Al-Khalili declared, "If the results prove to be correct and neutrinos have broken the speed of light, I will eat my boxer shorts on live TV." In February 2012, the source of the error was discovered. A loose fiber optic cable connecting the GPS receiver to the master clock had created a timing error of about 73 nanoseconds. There was also a second error related to oscillator timing that worked in the opposite direction. On July 12, 2012, the corrected results were published. The neutrinos arrived within the expected time frame, consistent with traveling at or very slightly below light speed. Einstein's theory survived. This episode actually demonstrates the strength of the scientific process. An extraordinary claim was made. It was subjected to rigorous examination. The error was found and corrected within about 6 months. And Al-Khalili's underwear remained uneaten. Science works. Now let's talk about the practical implications of light's cosmic speed limit, both the technology that depends on it and the constraints it places on our ambitions. We've already discussed GPS, but there's another medical technology that directly demonstrates Einstein's famous equation relating mass and energy. Positron emission tomography, or PET scans, works through matter-antimatter annihilation. A patient receives an injection containing a radioactive tracer, typically a glucose molecule tagged with fluorine 1,8. The fluorine 1,8 is unstable and emits positrons, which are antimatter electrons. When a positron encounters an ordinary electron, both particles are completely annihilated. Their combined mass converts entirely into energy in the form of 2 gamma rays. Each gamma ray carries exactly 511,000 electron volts of energy, which is precisely the mass energy of an electron or positron. The gamma rays fly off in exactly opposite directions, 180 degrees apart. PET scanners detect these coincident gamma ray pairs. By tracing the lines between coincident detections, the scanner can pinpoint where the annihilation occurred, mapping metabolic activity in the body. This is Einstein's E equals mc squared in medical action. Every PET scan performed in hospitals around the world is a demonstration that mass and energy are equivalent. At the other extreme of energy, the Large Hadron Collider at CERN accelerates protons to speeds where relativistic effects dominate completely. The LHC is a ring about 17 miles in circumference, buried beneath the border between Switzerland and France. Protons circle this ring 11,245 times per second, traveling at 99.9999991% of the speed of light. They're moving just about 10 feet per second slower than light itself. At this speed, the Lorentz factor is approximately 7,460. The protons have roughly 7,460 times their rest mass in kinetic energy. From the proton's perspective, the entire 17-mile ring appears to be only about 13 feet around, contracted by relativity. When protons traveling in opposite directions collide head-on, the collision energy reaches 14 tera-electronvolts. This is enough to create particles that are thousands of times heavier than protons, particles that haven't existed naturally since the first moments after the Big Bang. The Higgs boson, discovered at the LHC in 2012, has a mass of about 125 billion electron volts, more than 100 times the proton's rest mass. That mass is created purely from the collision energy. Energy becomes matter, exactly as Einstein's equation predicts. But the speed of light also imposes harsh limits on what we can do. And this is where the implications become sobering. Consider communication with spacecraft. Light travels at 186,000 miles per second. That sounds incredibly fast, but space is vast. The Moon is about 239,000 miles away. Light takes 1.3 seconds to make the trip. A round-trip communication takes 2.6 seconds. This was manageable during the Apollo missions, though it made conversations slightly awkward. There's always that pause, that lag, audible in the mission recordings. Mars is much farther. At its closest approach to Earth, it's about 34 million miles away. Light takes about 4.3 minutes to cross this distance. A round-trip message takes at least 8.6 minutes. At its farthest, when Mars is on the opposite side of the Sun, the distance grows to about 250 million miles. One-way light travel time stretches to 21 to 24 minutes. You ask a question, and the earliest you can possibly receive an answer is 42 to 48 minutes later. This isn't a technology problem we can solve with better radios. It's a fundamental feature of spacetime. The speed of light cannot be exceeded, so communication delays cannot be eliminated. The Voyager 1 spacecraft, launched in 1977, is now about 170 astronomical units from Earth. Where 1 AU is the distance from Earth to the Sun, that's roughly 15.6 billion miles. Light takes about 23.5 hours to reach Voyager 1. A command sent today won't arrive until tomorrow. Voyager 1 reached one full light day from Earth on November 15, 2026. At that point, the time for light to travel to the spacecraft and back exceeded 48 hours. And Voyager 1 is still within our solar system's outer reaches. The nearest star system, Alpha Centauri, is about 4.24 light-years away. That's roughly 25 trillion miles. Any message we send would take more than 4 years to arrive. A conversation spanning 8.5 years between exchanges is barely a conversation at all. The cosmic speed limit also determines what we can see. The universe is about 13.8 billion years old. Light that started traveling toward us 13.8 billion years ago has had that long to make the journey. This defines the edge of the observable universe. The most distant light we can receive is 13.8 billion years old. But here's where it gets counterintuitive. The observable universe has a radius of about 46.5 billion light-years, not 13.8 billion. How can we see objects farther away than light could travel in the universe's lifetime? The answer is that space itself has been expanding. Light that started its journey 13.8 billion years ago was much closer then. As it traveled, space stretched. The source of that primordial light has continued receding. By now, those early objects are 46.5 billion light-years away. The observable universe is therefore about 93 billion light-years in diameter. Beyond that boundary, light hasn't had time to reach us. There may be vastly more universe beyond what we can see, but we have no way to know. Even stranger, distant galaxies are receding from us faster than the speed of light. A galaxy beyond the so-called Hubble horizon, roughly 14 billion light-years away, is being carried away from us by the expansion of space at a rate exceeding light speed. This doesn't violate relativity. Special relativity says objects can't move through space faster than light. It says nothing about space itself expanding. The galaxies aren't flying through space at superluminal speeds. Space itself is stretching, carrying them along. Light from those galaxies, emitted now, will never reach us. They're beyond our cosmic horizon forever. We are fundamentally, irreversibly, cut off from those regions of the universe. Given how restrictive the light speed barrier is, it's natural to ask, is there any way around it? Scientists and science fiction writers have explored various possibilities. Most turn out to be impossible, but a few remain tantalizingly open questions. Let's start with what definitely doesn't work: quantum entanglement. When two particles become entangled, measuring one instantly affects what you'll find when measuring the other, regardless of distance. Einstein called this spooky action at a distance, and never fully accepted it. In 2022, the Nobel Prize in Physics was awarded to Elaine Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. Many people hear about entanglement and think it could enable faster than light communication. It cannot. Here's why. First, when you measure an entangled particle, you get a random result. You can't choose what outcome you'll get. Second, neither party can tell whether the other has made a measurement. The correlations between entangled particles only become visible when you bring the measurement results together and compare them, which requires normal, light speed, or slower communication. The spooky action creates correlations, not signals. There's a mathematical proof called the no communication theorem that demonstrates this rigorously. Quantum mechanics, despite its weirdness, respects the speed of light. The key insight is that entanglement creates correlations between measurement outcomes, but those correlations look completely random to each individual observer until they compare notes. Imagine two friends, each flipping a coin. Their coins are entangled, so that whenever one lands heads, the other lands tails. But from either friend's perspective, their coin still behaves randomly. They can't control which outcome they get. They can't send messages by flipping the coin in certain patterns, because they can't control whether they get heads or tails. Only when they meet up and compare results do they see the perfect anti-correlation. Quantum entanglement works the same way. Perfect correlation, but no ability to control or communicate. What about hypothetical particles that travel faster than light? In 1967, physicist Gerald Feinberg, published a paper titled Possibility of Faster-than-Light Particles in the journal Physical Review. He coined the term tachyon for such hypothetical particles from the Greek word for swift. Tachyons would have bizarre properties. They would have what's called imaginary mass, meaning their mass squared would be a negative number. They would always travel faster than light, just as ordinary particles always travel slower than light. Adding energy to a tachyon would slow it down. Removing energy would speed it up. They would approach the speed of light as an upper limit, just as we approach it as a lower limit from below. The problem with tachyons is causality. If tachyons existed and could be used to send information, they would enable signals to be received before they were sent in certain reference frames. This creates logical paradoxes that seem to break the consistency of physics. No tachyons have ever been detected. Most physicists believe they don't exist. It's worth noting that tachyonic fields do appear in certain quantum field theory calculations, but these don't represent particles that travel faster than light. They're a mathematical feature of unstable field configurations, like a ball balanced on top of a hill. The tachyonic nature indicates the system wants to roll down to a more stable state. A more interesting possibility comes from general relativity, the Alcubierre warp drive. In 1994, Mexican physicist Miguel Alcubierre published a paper titled The Warp Drive: Hyperfast Travel Within General Relativity in the journal Classical and Quantum Gravity. He was directly inspired by Star Trek. Alcubierre showed that Einstein's equations permit a configuration of spacetime where a bubble of flat space could move faster than light relative to distant observers. The bubble wouldn't be moving through space at superluminal speeds. Instead, space itself would be contracting in front of the bubble and expanding behind it. The ship inside the bubble would be locally stationary while the bubble carried it along. This technically doesn't violate special relativity. Special relativity prohibits objects from moving through spacetime faster than light. The Alcubierre drive moves spacetime itself. The catch is that creating such a bubble would require what physicists call exotic matter, matter with negative energy density. In ordinary physics, energy is always positive or zero. Negative energy density would require something unlike any known material. Initial calculations suggested the energy requirements were astronomical, equivalent to the mass of Jupiter converted entirely to energy. In 2011 and 2012, physicist Harold White at NASA showed that changing the bubble shape from a sphere to a torus could dramatically reduce the requirements. But dramatically reduced still means far beyond any technology we can imagine. There are other problems too. How would you steer such a bubble? How would you stop it? Light traveling at the front of the bubble couldn't reach the ship to bring information about obstacles ahead. And the bubble might accumulate extremely high-energy particles at its front edge, releasing them as a devastating blast when the drive disengaged. Wormholes represent another theoretical possibility. These are solutions to Einstein's equations that connect two distant points in spacetime through a shortcut, a tunnel through the fabric of reality. Einstein himself, along with Nathan Rosen, described these solutions in 1935. But the original Einstein-Rosen bridges are non-traversable. They collapse too quickly for anything to pass through. In 1988, physicist Kip Thorne and his student Michael Morris explored what it would take to create a traversable wormhole, prompted by a question from Carl Sagan for his novel Contact. They found that stabilizing a wormhole large enough to pass through would require negative energy equivalent to the mass of Jupiter. If wormholes could be created and stabilized, they would raise the same causality concerns as any faster than light travel. If one end of a wormhole is moved at high speed relative to the other, time dilation would cause the two ends to experience different amounts of time. Step through the wormhole, and you might emerge in the past. The logical paradoxes would remain. There is one way to exceed the speed of light that's completely real and doesn't violate any physics. Traveling faster than light in a medium. Light travels at 186,000 miles per second in a vacuum. But in other materials, it travels slower. The reason has to do with how light interacts with the atoms and molecules of the material. In water, light moves at about 140,000 miles per second. That's about 75% of its vacuum speed. In glass, about 124,000 miles per second, roughly 67%. In diamond, only about 77,000 miles per second, about 41% of vacuum speed. The ratio of light's speed in vacuum to its speed in a medium is called the refractive index. Water has a refractive index of about 1.33. Glass is around 1.5. Diamond is about 2.4, which is why diamonds sparkle so brilliantly. The high refractive index bends light sharply at the surface, creating internal reflections. But here's where things get interesting. A charged particle moving through water faster than light moves through water creates an electromagnetic shock wave, similar to a sonic boom. This phenomenon is called Cherenkov radiation, and it produces a characteristic blue glow. It was first systematically observed by Soviet physicist Pavel Cherenkov in 1934, and he shared the 1958 Nobel Prize for explaining it with his colleagues Igor Tamm and Ilya Frank. If you've ever seen photographs of nuclear reactor cooling pools, you've seen Cherenkov radiation. The water glows an eerie blue because electrons from nuclear reactions are traveling faster than light travels in water. These electrons are knocked loose by high-energy gamma rays from the reactor core, and they zip through the water at speeds exceeding light's pace in that medium. This doesn't violate relativity because the fundamental limit is the speed of light in vacuum. In a medium, that limit still exists as an absolute barrier. Particles can exceed the local speed of light in a medium while still traveling well below the vacuum speed of light. The electrons in reactor pools are moving at perhaps 60 or 75% of light's vacuum speed, well below the cosmic limit, but that's still faster than light travels through water. Sometimes things in space appear to move faster than light without actually doing so. Astronomers, observing certain quasars and radio jets, have measured apparent velocities exceeding 10 times the speed of light. The first such observations were made in 1969 and 1970 using very long baseline interferometry. One quasar, designated 3C279, has been observed showing apparent motion of up to about 10 times the speed of light. These are optical illusions created by geometry. When a jet of material moves at nearly the speed of light in a direction partly toward Earth, the light travel time from different points along the jet gets compressed in an unintuitive way. The jet appears to cover more angular distance than it actually does. The true speed of the material in these jets is around 99.7% of light speed. The superluminal appearance is a projection effect, not a violation of physics. One more striking phenomenon deserves mention. In 1999, Danish physicist Lene Vestergaard Howe achieved something that sounds impossible. She slowed light down to 38 miles per hour. Her technique involved passing light through an ultra-cold state of matter called a Bose-Einstein condensate. In this exotic state, near absolute zero, the interaction between light and matter becomes extreme enough to bring light almost to a standstill. 38 miles per hour is 20 million times slower than light travels in vacuum. In 2001, Howe went further. She stopped light completely, holding it in place for a measurable time before releasing it to continue on its way. In 2007, she demonstrated something stranger still, transferring a light pulse to a matter wave and back to light again. Howe once said, "We're getting the speed of light so low we can almost send a beam into the system, go for a cup of coffee, and return in time to see the light come out." These experiments don't violate relativity. The fundamental speed limit is light in vacuum. What Howe demonstrated is that the interaction between light and matter can be manipulated to produce astonishing effects. But even stopped light in a Bose-Einstein condensate isn't violating any laws. The photons are being absorbed and re-emitted by atoms, creating an effective slowdown. The cosmic speed limit remains intact. Let's step back and consider what the speed of light means for our place in the universe. We live in a cosmos of staggering size. The observable universe spans about 93 billion light-years, but everything beyond our cosmic neighborhood might as well be unreachable. Light from the Sun takes 8 minutes and 20 seconds to reach Earth, crossing 93 million miles. We see the Sun as it was 8 minutes ago. If the Sun suddenly went dark, we wouldn't know for over 8 minutes. The nearest star to our Sun is Proxima Centauri, 4.24 light-years away. That's roughly 25 trillion miles. Light takes more than 4 years to make the journey. Even if we could build a spacecraft traveling at 10% the speed of light, which is far beyond current technology, the trip would take over 40 years each way. The Milky Way galaxy spans about 100,000 light-years. Crossing from one side to the other, even at the speed of light, would take longer than modern humans have existed as a species. The Andromeda Galaxy, our nearest large galactic neighbor, lies 2.537 million light-years away. The light we see from Andromeda left when our ancestors were still developing the first stone tools. Any civilization in Andromeda looking at Earth now sees a planet without humans. This creates a peculiar kind of cosmic isolation. We can see the light from billions of galaxies, but we can never visit them, never communicate with anyone who might be there, never receive a reply within any human lifetime or any 1,000 human lifetimes. Even within our own solar system, the speed of light creates communication challenges that grow with distance. Mars can be anywhere from 4 to 24 minutes away at light speed, depending on orbital positions. Managing a rover on Mars means sending commands and waiting 8 to 48 minutes to see the results. For any crewed mission to Mars, the communication delay means the astronauts must be largely self-sufficient. There's no calling Houston for immediate help. Help, even at the speed of light, is always minutes away. The speed of light also shapes what we can know about the universe. Because light takes time to travel, looking at distant objects means looking back in time. When we observe a galaxy 1 billion light-years away, we see it as it was 1 billion years ago. Telescopes are time machines. This is useful for cosmology. We can study how the universe evolved by looking at objects at different distances. But it also means we can never see the universe as it currently is. Our view is always a composite of different ages, more recent nearby and more ancient farther away. There are events happening right now in distant galaxies that we will never see, because the universe's expansion is carrying those galaxies away from us faster than light. Light emitted by those galaxies today will never reach us. We are forever cut off from most of the universe's current state. The cosmic speed limit also affects the search for extraterrestrial intelligence. If an alien civilization exists on a planet orbiting a star 100 light-years away, any signal they send us takes 100 years to arrive. Any reply we send takes another 100 years to get back. A single exchange takes 2 centuries. If the civilization is 1,000 light-years away, still within our own galaxy, a back-and-forth communication spans 2,000 years. The Roman Empire would have needed to start the conversation for us to be receiving replies now. And 1,000 light-years is practically next door on cosmic scales. The Milky Way is 100,000 light-years across. A message sent to the far side of our own galaxy would take longer than modern humans have existed to get a reply. This creates what some scientists call the Great Silence. Even if the galaxy is teeming with intelligent life, the vast distances and the speed of light might make contact essentially impossible. 2 civilizations might exist simultaneously in the Milky Way, both searching for each other, both sending signals into the void, and never connect because their signals haven't had time to cross the intervening space. The Fermi paradox, the question of why we haven't detected alien civilizations despite the apparent likelihood they should exist, has many proposed solutions. One of them is that the speed of light makes interstellar communication and travel so difficult that civilizations remain isolated even in a galaxy full of intelligent life. Perhaps someone is out there, but the universe is simply too big and the speed limit too strict for us to ever know. This isolation might be the natural state of intelligent beings in the universe. Not because we're alone, but because the cosmic speed limit creates unbridgeable gulfs between stars. Every civilization might be an island, visible to others through telescope, but forever beyond reach of conversation or visit. If that's true, then the speed of light isn't just a physical constraint. It's a fundamental feature of existence in this universe, a kind of cosmic loneliness built into the structure of space-time. The speed of light doesn't just constrain what we can do. It challenges the deepest assumptions we have about the nature of reality. And these aren't abstract philosophical puzzles. They're direct consequences of experimental facts. Think about what we've established. Time genuinely runs slower for moving objects. Space genuinely contracts. Events that are simultaneous for one observer are not simultaneous for another. These aren't approximations or simplifications. They're how the universe actually works. But if that's true, then many of our basic assumptions about reality must be wrong. We naturally think of time as a river flowing at a constant rate, carrying us all forward together. We think of space as a fixed stage on which events play out. We think of now as a single moment that everyone shares, spreading across the entire universe at once. Relativity tells us none of this is true. Consider what the relativity of simultaneity really means. If there is no universal now, if different observers legitimately disagree about what is happening at this moment in distant places, then what is the present? Einstein himself took a radical position on this question. He came to believe in what philosophers call the block universe, or eternalism. In this view, past, present, and future all exist equally. Spacetime is like a 4-dimensional block of ice, with all events frozen in place. Our experience of now moving through time is an illusion, a peculiarity of consciousness, not a feature of physics. Einstein expressed this view most movingly after the death of his lifelong friend Michel Besso in 1955. Einstein wrote to Besso's family, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion." Einstein died just weeks later. If his block universe view is correct, Besso and Einstein both still exist, frozen in the space-time of their lifetimes, as real as any moment we call present. The philosophical argument for the block universe draws directly from special relativity. Consider the Andromeda paradox again. Two people walking past each other on a sidewalk disagree about what is happening now on Andromeda. For one, a certain event hasn't happened yet. For the other, it has. Now ask, which events are real? If we say only present events are real and future events haven't happened yet, then we have a contradiction. An event can't both have happened and not yet have happened. The only way to avoid this contradiction is to accept that both events, and indeed all events across all of space-time, are equally real. Past, present, and future are all equally existent. What differs is only our perspective on them. Not all philosophers accept this conclusion. Some argue that there are ways to recover a meaningful present moment, even in relativity, perhaps by privileging a particular reference frame or by accepting that reality is perspectival. These debates continue in philosophy departments and physics conferences around the world. The growing block view, for example, accepts that the past and present are real, but holds that the future is not yet determined. Under this view, the block of reality grows as time passes, with new events being added to the past. But this view struggles to explain why any particular moment should be the edge of the growing block, especially when relativity tells us that different observers would place that edge at different points. Another approach, called Presentism, insists that only the present moment is real. The past has ceased to exist and the future doesn't exist yet. This matches our intuitive sense of time, but it seems hard to reconcile with the physics. If only the present is real, who's present? The person walking toward Andromeda? The person walking away? What makes one perspective privileged over the other? Some physicists have proposed that relativity might be incomplete, that there could be a hidden preferred reference frame that defines a universal present, even if we can't detect it experimentally. But this seems like adding unnecessary complexity to explain away an uncomfortable conclusion. The honest answer may be that we simply don't know yet. The relationship between physics and the fundamental nature of reality remains one of the deepest unsolved problems in philosophy. What we can say is that the speed of light forces us to take these questions seriously. It's not just speculation. The experimental facts demand that we revise our intuitive picture of time and space. But it's striking that a measurement made by a Danish astronomer watching Jupiter's moons in 1676 would eventually lead to questions about whether the future already exists. The speed of light connects the everyday to the cosmic. Another philosophical puzzle concerns the nature of the speed limit itself. Why is the speed of light what it is? Why 186,282 miles per second rather than some other number? The answer, as far as physics can tell, is that it simply is. The speed of light is a fundamental constant of nature, not derivable from anything more basic. It appears in the equations of physics as a given, not as a consequence. Some physicists have speculated about varying the speed of light to see what would happen. A universe with a different value of c would have different chemistry, different stellar physics, different everything. In most such universes, complex structures like atoms and life could not exist. Our universe happens to have a speed of light compatible with our existence. This observation leads some to anthropic arguments. Perhaps there are many universes with different constants, and we necessarily find ourselves in one compatible with observers like us. Others find such arguments unsatisfying, hoping for a deeper explanation of why the constants have the values they do. For now, the speed of light remains a mystery at the deepest level. We know what it is. We know how it shapes physics, but we don't know why it has the particular value it does. There's also a philosophical puzzle about the light cone itself. Inside your light cone, events are causally connected to you. Outside, they are not. Events in the elsewhere region can't affect you, and you can't affect them. They exist, but in a realm forever beyond your influence or knowledge until they enter your past light cone. This means that right now, somewhere in the universe, events are occurring that will someday affect you, but that you currently have no access to whatsoever. And there are events that have occurred that you don't know about yet, that are racing toward you at the speed of light, whose effects you will experience in the future but cannot yet anticipate. In a sense, your light cone defines the boundaries of your existence. Everything that is you, everything that has made you, everything you will ever influence, lies within that cone. Everything else might as well be in a different universe. Throughout this documentary, we've traced humanity's 400-year effort to measure the speed of light and understand its consequences. Let's bring it all together. In 1676, Ole Rømer watched Jupiter's moons and realized that light takes time to travel across space. His calculation was off by about 25%, but he proved the essential truth. Light, however fast, is not instantaneous. It took 53 years for Bradley to independently confirm this discovery. Over the next 2 centuries, Fizeau, Foucault, and Michelson refined the measurements with increasing precision. By 1887, Michelson and Morley had shown that light travels at the same speed in all directions, regardless of Earth's motion. The ether didn't exist. Something strange was going on. In 1905, Einstein explained what? He accepted the constancy of light speed as a fundamental feature of nature and showed that time and space must be flexible to accommodate it. The resulting theory of special relativity revealed that moving clocks run slow, moving objects shrink, and simultaneity is relative. In the decades since, every prediction of relativity has been confirmed experimentally. Atomic clocks flown around the world show exactly the time differences Einstein predicted. Particles in accelerators live longer than they should because their time runs slow. GPS satellites require constant relativistic corrections to function. The equations aren't just mathematically elegant, they're the accurate description of how reality works. The speed of light isn't merely an interesting constant. It's woven into the structure of spacetime. It connects mass and energy through Einstein's famous equation. It defines the boundary between what can influence what. It determines what we can see and what remains forever hidden. And it poses limits that we may never overcome. We can approach the speed of light, but never reach it. We can look at distant galaxies, but never visit them. We can send messages to the stars, but never expect a timely reply. Some find this depressing. The universe is vast and mostly unreachable. Even our nearest stellar neighbors are effectively isolated from us by the tyranny of light speed. But there's another way to see it. The speed of light isn't just a barrier. It's a window into the deepest structure of reality. It teaches us that space and time aren't the fixed stage we thought they were, but flexible, interconnected, responsive to motion and gravity. It shows us that mass and energy are two faces of the same coin. It reveals that causality itself has a speed limit, preserving the logical order of events across the cosmos. For thousands of years, humans assumed that time flows uniformly, that space is absolute, that distance is the same for everyone. The speed of light showed us that none of these assumptions are true. Our everyday intuitions, evolved on a small planet at walking speeds, simply don't apply to the larger universe. Understanding this doesn't diminish our place in the cosmos. It deepens it. We are creatures who evolved to see the world in simple terms, and yet have developed the tools, mathematical and experimental, to perceive truths far beyond our sensory experience. We can't feel time dilation, but we can measure it. We can't see length contraction, but we can calculate its effects. We can't travel at relativistic speeds, but we can understand what would happen if we did. In 1946, near the end of his life, Einstein reflected on that thought experiment that had troubled him since he was 16 years old. What would it be like to chase a beam of light? He never did get to ride alongside a light beam. No one ever will. But in trying to answer that question, he discovered something deeper than any journey could reveal. He discovered that the universe is stranger, more subtle, and more beautiful than anyone had imagined. The speed of light doesn't just tell us how fast light travels. It tells us what kind of universe we live in. And that universe, it turns out, is far more interesting than the simple, intuitive one we thought we knew. So the next time you look up at the stars on a clear night, remember what you've learned tonight. Those points of light scattered across the darkness are not just lights. They're distant suns, massive balls of fusing hydrogen, each one potentially hosting its own system of planets and moons. They're light years away, separated from us by distances so vast that the light entering your eye right now has been traveling for years, decades, centuries, or even millennia. Some of that light began its journey before you were born. Some of it left its star before your grandparents were born. Some of it has been traveling since before there were any humans at all. You're connected to those distant stars across the vast distances of space and time, linked by photons that have crossed the cosmic void to reach you. The universe is large beyond comprehension. You are small, a single person on a single planet. But you're here, and you can understand, at least conceptually, if not intuitively, what the speed of light really means. You can grasp that the universe is measured in these vast units, that space is filled with distances that dwarf anything in human experience, and that understanding, that ability to comprehend your place in the cosmos, is something worth holding on to. Consider the journey we've taken in this documentary. We started with ancient philosophers debating whether light was instantaneous or finite. We watched Galileo fail to measure light's speed with lanterns on hilltops. We followed Roma as he tracked Jupiter's moons and made his audacious prediction. We stood with Fizeau as his toothed wheel caught returning light for the first time. We felt the frustration of Michelson and Morley as their careful experiment found nothing at all. And then we watched as Einstein, a 26-year-old patent clerk with no laboratory and no academic position, took that nothing and built from it a completely new understanding of space and time. An understanding so radical that even now, over a century later, it still feels counterintuitive. An understanding so accurate that we stake our lives on it every time we use GPS. The story of the speed of light is a story about human curiosity and persistence, about asking questions that seem unanswerable and finding ways to answer them anyway, about being willing to follow the evidence wherever it leads, even when it leads to conclusions that violate everything we thought we knew. The speed of light is 186,282 miles per second. It's a number, precise and exact, now fixed by definition. But what that number represents, the cosmic speed limit, the boundary of causality, the weaver of space-time, is something far grander than any number can convey. The speed of light breaks our everyday reality. But in doing so, it reveals a deeper reality, one where time bends, space shrinks, and the cosmic speed limit preserves the order of cause and effect across all of creation. That's not a limitation. That's a revelation. And perhaps most importantly, the speed of light connects us to the cosmos in a profound way. Every photon that enters your eye has traveled at that exact speed. The light from the sun, the light from distant galaxies, the light from the cosmic microwave background at the edge of the observable universe, all of it has raced across space at exactly 186,282 miles per second. Not a mile per second faster, not a mile per second slower. That constancy, that reliability, that unchanging nature of light speed is one of the few things in the universe you can absolutely count on. And that's the true meaning of the speed of light.